Okay, so I'm going to demonstrate lab number 4 for you. And so in this lab, we're working with an operational amplifier, as you can see here. So, you know, we've got part number 741, but really, you know, the operational amplifier works in a very typical way, where it takes in a signal and it boosts it, and so this can be used to amplify weak signals or transmit weaker signals over a longer distance where they might dissipate too much for us to read them, or to help us kind of read variations in a signal a little bit easier because we're not working with such small values. And so in this case, the amplifier that we're working with is an inverting amplifier. And so I'll kind of describe what that means as we go through this and demonstrate how we can see that it's an inverting amplifier. Quickly, I'm going to show you this table. So as we will be closing up some of these switches, we will change these values, and you can see that as we go up the switches from A to D, we're actually going to increase in the output voltage of this amplifier. So I'm going to now demonstrate this. So you've got a 5 volt and a negative 15 volt coming in here. And so this is creating a differential within this. And basically what's happening is the power that's being supplied to each of these terminals, as well as fed back into this terminal, it's basically amplifying the differential, I think, between what we've got coming in as well as what is going on from here to here. And yeah, so we'll see kind of how that works. So I'm going to start, as you can see right at the start, we've got 4.4 millivolt. So essentially there's no voltage in this circuit at the moment, and anything that's coming to the output is kind of just leaking through. You know, it's very, very low voltage. If we now close A, you'll see we got negative 2.45 volt. And so the reason it's negative is because we are feeding it back into this negative terminal. And so it's creating a negative operational amplifier, or an inverting amplifier, which is why we see, positive supply over here, but we're outputting a negative voltage over here. So I'll kind of go up to the list now. We open A and close B, we get negative 1.87, so it's gone up a little bit. Close A now, negative 2.5. And if we continue in this way, 2.85, 3.6, 3.95, 4.37, 4.995, 6.2. And so you see some of our most dramatic jumps kind of happen when A is turned on. And that's because we are going through so many resistors with A, whereas these ones really aren't. And so that's just kind of amplifying that difference a little bit more, as well as it's also coming into this positive terminal when we've got A closed. So that's where you're going to see more difference, and thus more voltage being output from our amplifier. B and A, 6.89, 7.4549. Oh, yep, 7.85, 8.6, and 9.36. And so yeah, as it increases, as we close more of these, we are inverting more and more, right? We're amplifying more and more. So that's why we see our voltage keep on increasing as we go on. And so, yeah, that's kind of the function of the operational amplifier. And now we can show the second part of this lab, where we've connected our operational amplifier to the binary counter. That's a 74LS393D, and we've got that connected to just a function generator or a digital clock. And so we can visualize this. As you can see, just started like that. We've got this sawtooth pattern, and I'll kind of explain why that's happening. So our binary counter, as we know, is going to be going in a typical binary count, right? So if we have 4 binary digits, it starts off 0000, and we have 0001, 0010, 0011, 0100, 0101, 0110, 0111, 1000, and so on, right? So that's our typical binary count. Well, when this is coming through our outputs, that's going to act as these switches. So where we saw kind of the effect of that gradual increase in output voltage, that's exactly what we'll see from these. Although I think it is, well, yeah, so it's increasing, but we're going to see it in the negative side because, again, inverting amplifier. And so that's why on these sawtooth patterns, we see it going down. If it wasn't inverting, we would see it going up. But because it's an inverting amplifier, we're going to watch it go down because it's becoming more and more negative, but it is a higher voltage at the bottom, obviously, than the center line, which is 0. And so then when you see these big spikes, that's when it's going back to 0. And so, everything's opening up and we have basically no voltage in the circuit again, like when we looked at the last one with them all open and we had the 4.7 millivolt. That's basically what's going to be happening here, and that's what this jump back is. And so if we hit play on this, let's see as it goes on, each of these numbers, and then jump back up. And so if we counted the number of steps as well, actually, maybe we can do that. So we get 1 step, 2 step, 3 step, 4 step, 5 step, 6 step, 7 step, 8, 9, 10, 11, 12, 13, 14, 15 steps. And doesn't that make sense? Because there's 15 steps in, a 4-digit binary number, essentially 15 values. I think they're, it totally makes sense that that's how many steps we would see, and that's why we would see those. So, like in an earlier lab, we used a hexadecimal counter, and we would have had 16 numbers coming out. We would probably see 16 steps, but yeah, using this 4-digit binary counter, it makes sense why we see this number of steps, and then that shoot back up. Yeah. And so it's a very interesting pattern. This is how we can create, very well regulated sawtooth patterns. So if there's a device that requires something like this, using the binary counter and the operational amplifier in this configuration, we can create a very well timed and well ordered output for a device. And yeah, I think that demonstrates the second part as well. So that's the operational amplifier lab. Thank you.